great to be able to meet in person, and we're hoping to, like with other classes, to use this time together to take advantage of the opportunity to converse in a way that we wouldn't be able to with this just a strict lecture format. So last lecture we had seen a glimpse of a couple sorts of modeling. The two types of modeling we had examined were exemplified by two packages we looked at, components of packages. The first is this. What package is this? Vensim. And what sort of modeling is this representative of? System dynamics, yeah. So here we have stocks, we have flows. The stocks represent accumulations or state, the current status of the system. In this case, people are divided between susceptible, infected, and recovered. And the number of people in a given category evolves over time according to flows into and out of that category. And it turns out that these values of the stocks are purely determined by the flows aside from an initial value in the stock. So you just have to specify for these stocks an initial value, and after that, knowing the rate at which things are coming in, the rate at which things are going out, will tell you how that stock changes over time. Now, a lot of the trick, though, is that the values of those flows depend in turn on the values of the stocks. So we have a system like this that can be depicted with stocks and flows, often in a quite simple fashion, but whose evolution over time can be quite quite variegated. So we can see behavior like this, in this case, sort of an outbreak. And it turns out that within the context of system dynamics, there's a big attention played to feedbacks. And if we were to draw the feedback structure associated with this diagram, there'd be a variety of feedbacks operating, both so-called reinforcing feedbacks which amplify a given change. For example, the more infectives there are, larger fraction of people around that are infected, and therefore the more people that can spread that infection to others, and there's a positive feedback here that will lead to even more people become infected. So it goes from one person being infected to 2, to 4, to 8, over a period of days, weeks, etc. But there's other feedbacks that are what are called balancing feedbacks that limit how far that can go, that are regulatory in nature. In other words, they keep the system more in balance. For example, as there's more and more infectives, there are more and more people get infected, there are fewer and fewer susceptibles, people who can still get infected. So there's a limit on the number of people that can get infected if no one's coming into the population associated with this total number of susceptibles, or the total size of the population. And at some point, that starts to really make an impact. So at first, the infection takes off, driving because of this positive feedback, this amplifying feedback. It goes faster and faster, rising faster and faster at first. But eventually it starts to slow down because each infective is surrounded by more and more people they can't infect. More and more people around them have already been infected. Maybe they've recovered, maybe they're still infected, but they can't infect them as a new infected. And so it starts to turn around, and eventually it reaches the point, starts to slow down how efficient it can get in transmitting. Eventually it reaches the point where the stock starts to actually decrease, the number of infectives. And just knowing what we do now, if we know there's some number of people coming in per week who are getting infected, some number of people recovering per week, when would the value, the number of people who are infected, start to go down? If what? Under what conditions? Well, if the number of recovered people per week is greater than the number of infected people per week. More people recovering than people are leaving faster than they're coming in. And the population of the room is going to decrease. Right? And so that's when it starts to decrease, and eventually it sort of gets slower and slower, and that decreases, and fewer infected as more and more recovered. So there's a feedback structure behind this. And in fact, within system dynamics, there's strong attention paid to that. And one of the features of NSIM is that you can actually request an identification of various loops within the model, various feedbacks that apply within this model that are governing that structure. It's a very, very powerful way of understanding the system. Very amenable to sort of a high-level understanding of what's going on. And we'll actually see, ladies and gentlemen, that understanding, the way of parsing apart what's going on in terms of feedbacks, in terms of stocks and flows. We'll actually apply that outside of system dynamics. We'll apply it to models that happen to be agent-based in their description. So it's a general perspective that can be carried over not just for stocks and flows, but for other mechanisms. So I'll just